Thank you. First of all, I'd like to thank the organizer for giving this wonderful opportunity. I'm very happy that I can talk here in front of this wonderful audience. My talk is a joint work with Jonathan Goodman. Jonathan is now in Poland. Okay, so today I first start from Shannon's fundamental work. So Shannon studies the following problem. We would like to transmit information by using signals whose frequency is limited between plus minus W, for example, telephone signal. And suppose the signal has a power P, and of course every communication has some noise. So suppose the noise is Gaussian and density N. And Shannon wants to clarify how much information we can send. And the answer is the following. Shannon found that the answer is given by the quantity called capacity. And in this case, capacity is given by this beautiful formula. Okay, so this is just a motivation section. So if you don't know information theory well, please don't worry. This is just a motivation. But here I just want to emphasize that the bandwidth W, so we use a signal whose frequency is limited between plus minus W. This W is a very crucial parameter in the communication over band limited signals. This is an important point. And in my talk, we study an analogous problem in topological dynamics. Okay. So what are dynamical systems? In my talk, dynamical system means that a pair xt. X is a compact metrizable space, and T is a homeomorphism of T, a homeomorphism of X. This is dynamical system in my talk. And the basic example in my talk is the following: shift on the Hilbert cube. Hilbert cube is an infinite dimensional cube. So this 0, 1 is an interval, standard unit interval. And we consider the infinite product of the interval indexed by Z and consider the shift map. So shift, so here N, and this is N plus 1. So this is called shift map. Then the pair, this pair Hilbert cube and shift becomes a dynamical system in this definition. Okay, this is, in some sense, the most basic example. Okay, now we study, we can ask the main problem, so-called embedding problem. Given a dynamical system xt, when can we embed it into the shift on the Hilbert cube? Here, the map, a continuous map f from x to Hilbert cube is called an embedding of a dynamical system if f is a topological embedding commuting with the actions. So here, f is a map and sigma is a shift, this shift, and T is the original dynamics. Very trivial, almost trivial example of the following irrational rotation. The space is a circle, and the map dynamics is a so-called irrational rotation. Then we can check that the following map is an embedding of a dynamical system. This means that given this right-hand side data, we can recover x. This is the meaning of embedding. But this case is very simple. This is a very easy example. So what is obstruction of the embedding? The obvious obstruction comes from periodic points. Namely, if a dynamical system xt has many periodic points, then it cannot be embedded into the shift on the Hilbert cube. For example, consider the shift on the, in some sense, this is an infinite product with a square. So in some sense, twice bigger than Hilbert cube. Then the shift on this system cannot be embedded into the shift on the Hilbert cube because consider the fixed point set of this system. Then the fixed point set of this system can be naturally identified with the squares. And on the other hand, the fixed point set of this Hilbert cube system is identified with the unit interval. And obviously, square cannot be embedded into the interval. So this system cannot be embedded into this system. So this example shows that periodic, so fixed points set and also periodic point set becomes obvious obstruction for the embedding. And somewhat surprisingly, Jaworski found that this is the only obstruction for finite dimensional systems. This is a surprising theorem, proved more than 40 years ago. Suppose X is finite dimensional. This means that topological dimension of X is finite. And Xt has no periodic points. Then we actually embed it into the shift on the Hilbert cube. This is Jaworski's theorem. For example, consider the arbitrary finite dimensional compact manifold M and consider arbitrary homeomorphism of F. And take the product system, M and irrational rotation. Then if we multiply irrational rotation, then this product system has no periodic point. And also this is finite dimensional. So Jaworski's theorem implies that we can embed this system into the shift on the Hilbert cube. So here, F is an arbitrary map. So might be very crazy map. But every messy phenomena can be absorbed into the infinite dimensionality of Hilbert cube. So I think Jaworski's theorem is surprising. But so Jaworski's theorem is very nice, but also obviously it poses a new question. So how about infinite dimensional systems? So why we need to assume finite dimensionality? This is the next question. And Josef Auslander asked the following question. Can we embed every minimal dynamical system into the shift on the Hilbert cube? This is the next question, asked about 30 years ago. Here, dynamical system is called minimal if for every point x, its orbit is dense in x. For example, the irrational rotation is minimal. Why Auslander asked this question? The point is that minimal system has no periodic point unless x is a finite set. And the finite set case is a very trivial case for this embedding problem. So this question, so morally speaking, this question means that we want to consider the simplest case having no periodic point and ask what happened. This is the meaning of the Auslander's question. Do you understand this question? And this Auslander's question was solved by Aaron Lindenstrass and Benjamin Weiss by using the theory of mean dimension. And here's one remark. We can also discuss the problem of embedding of dynamical system into the shift on the infinite product of n-dimensional cube. Everything can be generalized into this setting without any difficulty, but just for simplicity of the notation, I consider the case of n equal 1 today in this talk. Okay, so next I need to explain what is mean dimension. This was introduced by Gromov 20 years ago. It is a topological invariant of dynamical systems, and morally speaking, it counts how many parameters. So how many parameters we need to describe an orbit in a dynamical system. For example, consider shift on the Hilbert cube. And intuitively, this system has one parameter for each integer. So its mean dimension is 1. And of course, this is non-rigorous, so the rigorous definition is as follows. Take a positive number epsilon and a compact metric space xd. A continuous map from x to some topological space y is called an epsilon embedding if for every point y, its image has diameter less than epsilon. So the picture is the following. This is the picture of the epsilon embedding. So here x is this tube, and y is this plane, and we consider some map F. And this epsilon embedding condition means that for each point y, its image has a diameter less than epsilon. So this means that if we ignore some small error epsilon, this map F looks like an embedding. Okay? Then we define epsilon width dimension of a compact metric space X as follows. This is the minimum integer n such that there exists an n-dimensional polyhedron P and the epsilon embedding from X to P. So, this polyhedron means just a simple shell complex. So roughly speaking, this means that we want to understand the space by using a polyhedral approximation. And this polyhedral approximation has some error bounded by epsilon. And we ask how many parameters we need in this polyhedral approximation. This is the meaning of this width dimension. And the following classical fact is known. Probably this is due to Urizon. The topological dimension of X is given by the limit of this number. If you don't know the topological dimension, the definition of topological dimension, just think that this is a definition of topological dimension. But there is just one non-trivial point. So this number is a metric invariant, so it depends on the distance d, but the topological dimension is a topological number. So if we take the limit, it becomes a topological invariant. This is the important point. Okay, this is a classical dimension theory. So next, I introduce a mean dimension. Suppose we have a dynamic, so given a homeomorphism T, then we can define new distance dn for each integer n by this formula. So this means that we want to estimate the distance between orbits. Then we define mean dimension by this way. So this is a width dimension, epsilon width dimension, and we put new distance dn here. And we want to know the linear growth rate of this number with respect to n, and take the limit. And next, take the limit with respect to epsilon. And we can check that this limit always exists, and this becomes a topological invariant. So topological means that, so this definition uses a distance d, but the limit value is independent of the choice of a distance. This becomes a topological invariant of dynamical systems. This is called mean dimension. For example, if the system is finite dimensional, then mean dimension is 0. So mean dimension has a meaningful only for infinite dimensional systems. And for example, consider the infinite product of n-dimensional cube and the shift. Then its mean dimension is n. And intuitively, this means that the mean dimension of this system is given by this formula. So it is a ratio between the dimension of the space and the order of z. And heuristically, dimension of this space is n times the order of z. So we cancel and we get n. This is the intuitive meaning. Of course, this is non-rigorous because the order of z is infinite. But the concept of mean dimension provides a rigorous mathematical meaning, this kind of heuristic idea. Okay, so this is a definition of mean dimension. And why this is important in the embedding problem? And in some sense, the reason is very simple. If a dynamical system X can be embedded into another system Y, then mean dimension of X is bounded by the mean dimension of Y. This is a trivial consequence of the definition. But then, if the mean dimension is strictly greater than 1, then we cannot embed it into the shift on the Hilbert cube, because the shift of the Hilbert cube has mean dimension 1. Then, Lindenstrauss and Weiss prove the following. For every non-negative real number C, there exists a minimal system of mean dimension exactly equal to C. Then as a direct consequence, there is a minimal system which cannot be embedded into the shift on the Hilbert cube. For example, we can take a minimal system whose mean dimension is equal to 2. So this corollary negatively solves the Auslander's question. This is a theorem, Lindenstrass and Weiss. And surprisingly, Lindenstrass went further. He proved a partial converse. Suppose that minimal system xt has mean dimension smaller than 1/36. Then we actually embed it into the shift on the Hilbert cube. So for minimal system, in some sense, essentially mean dimension determines everything. If mean dimension is sufficiently small, we can embed it in the shift on the Hilbert cube. This is an amazing theorem. But also, of course, this number looks strange. So 1/36 looks a strange number. So Lindenstrass asks, what is the optimal number? Can we improve this number? This is Lindenstrass' question. This was asked in his PhD thesis. And our main result solves this problem. It follows our main result. Suppose a minimal system has mean dimension smaller than 1/2, then we can embed it into the shift on the Hilbert cube. And this 1/2 is optimal because Lindenstrass and myself prove that there exists a minimal system such that mean dimension is exactly equal to 1/2, and it cannot be embedded into the shift on the Hilbert cube. So this 1/2 is optimal number. This is our main theorem. Okay, do you understand the statement of the theorem? So far we have discussed only a very abstract topological dynamics. In some sense, there is seemingly no connection between communication theory or information theory, but suddenly communication theory appears. So we can reformulate the question into the language of signal processing. So take a point x in the Hilbert cube. So this point, in some sense, it is a signal. It is a sequence of real numbers. So this is a discrete signals. So the embedding problem asks how to encode dynamical systems into discrete signals. This is, in some sense, reformulation of the problem. And this reformulation is, in some sense, useful because we can use a different object, so continuous signals. Our approach is the following. First, we encode dynamical systems into continuous signals. And then by using sampling, we convert these continuous signals into discrete ones. This is our approach. So this is a preparation for our signal processing setting. Take a two real number A and B. A bounded continuous function from R to C is said to be boundary limited between A and B if its Fourier transform is supported between A and B. This number B minus A is called bandwidth. For example, sine 2 pi t and cosine 2 pi t are boundary limited between plus minus 1. And in Japan, the standard telephone signals are boundary limited between plus minus 3.6 kilohertz, I think. This is just, and this slide is just a digression. So actually, how to construct boundary limited functions. And this is a very classical subject, essentially solved by Perry and Wiener. Let's take a positive number c. A bounded continuous function phi is boundary limited between plus minus c if and only if it becomes the entire function satisfying this growth condition. And for example, consider the so-called sinc function. This is sinc function, and this has this infinite product expansion. This is the entire function, and its growth is this. given by this number. So by this theorem, this is bound limited between plus minus 1/2. And we can construct many examples of bound limited functions by using similar infinite product. So this is a classical connection between signal analysis and complex analysis. Okay, so this is a digression. Okay, let's come back to the main point. So for two real number a and b, we define the space BAB. This is a set of bounded continuous functions which are bound limited between a and b and has L infinity known bounded by 1. And this becomes a compact space under this distance. This distance looks a bit technical, but this is just its topology is very simple. Its topology is so-called compact open topology. And we define the shift on this space. Shift is just this way. So here t, and this is here t plus 1. Then the pair BAB and sigma becomes a dynamical system in our definition. So this is a compact metrizable space, and this is a homeomorphism. And we can calculate its mean dimension. Its mean dimension is given by the twice of bandwidth. Then our main theorem 2 is the following. Suppose xt is a non-trivial minimal system and its mean dimension is smaller than the bandwidth. Then we can embed it into the shift on this BAB. Here, non-trivial just means that X is an infinite set. The main theorem 1, so the main theorem 1 is this theorem. So this is answer to Linde's first question. So this main theorem 1 follows from main theorem 2 by the classical sampling theorem. If the bandwidth is smaller than 1, then this sampling map becomes an injection. So by using main theorem 2, we can encode dynamical system into band-limited functions. And by using a sampling theorem, we can convert these band-limited functions into discrete signals. Then we get main theorem 1. This is the approach. Okay, do you understand the statement? Okay. Sorry. Okay. So next, I want to explain why continuous signals are more flexible than discrete ones. So continuous signals is more flexible than discrete ones, so we can prove the theorem. So what is the advantage? And then for explaining this advantage, I need to introduce a bit more technical theorem. So let phi be a factor map from x to y. This means that xt and ys are both dynamical systems, and this map phi is a continuous surjection commuting with actions. This is the meaning of factor map. Then under this setting, if y is a non-trivial minimal system and x has mean dimension less than b minus a, then xt can be embedded into the product of BAB and y. This is a bit technical statement, but in some sense, this is an expository reason. So this statement makes me easier to explain why continuous signals are more flexible than discrete ones.
So you assume xt has a factor map to y,
yes? Yes. So given a factor map and suppose these assumptions. Okay, and I want to explain how to prove main theorem 2 by using main theorem 3. And recall the statement of main theorem 2. if xt is a non-trivial minimal system and has mean dimension smaller than the bandwidth, then it can be embedded into the system of BAB. The point is that in this statement, we don't have factor map. We have only a x. Okay, so here is the assumption. So mean dimension is smaller than the bandwidth, and this is the picture, the interval between A and B. First, we take the real number CD such that this lengths between A and C are greater than the mean dimension. So these C and D are very close to B. And next, we take a generic equivalent continuous map from X to DB. So DB is here. So I don't want to explain the precise meaning of this generic. But anyway, so we take some generic map. Please don't ask it. So then we can check that the image Y becomes a non-trivial minimal system. Here, the point is a non-trivial. So the factor of minimal system is always minimal. This is trivial. But sometimes it becomes a finite set. So we want to exclude such case. But if we take a generic map, then it becomes a non-trivial minimal system. We can check that. Then we have a factor map. So we can apply main theorem 3 to this setting. We apply main theorem 3 to this factor map. And so we have this mean dimension condition. So we can embed xt into the product of BAC and Y. But now Y is a subsystem of this BDB. So this is a subsystem of this system, BAC cross BDB. On the other hand, here, so this AC is this interval, and DB is this interval. And the point is that this AC and DB has no intersection. So trivially, this right-hand side can be embedded into BAB by this just addition. Because there is no interaction between these frequencies and these frequencies. Okay, then this proves main theorem 2. This argument is very simple, but it just shows why continuous signals are more flexible than discrete ones. The point of this proof is that we can take two disjoint bands between AC and DB. This disjoint bands trick is possible because we can consider continuous signals. So frequency can vary continuously. On the other hand, discrete signals don't have this kind of flexibility. So this is the most important advantage of continuous signals. Okay, and this is the final slide. So now I think the embedding problem for minimal systems are well understood. But the problem for general, namely non-minimal systems, still remains open. And the guiding conjecture is the following. If a dynamical system satisfies the following condition, namely the mean dimension is smaller than 1/2, and for each integer n, so for each natural number n, the set of n periodic point has dimension bound by this way. So this is a dimension of the periodic point set, and we take the ratio, we consider the ratio between this dimension and n. And suppose it is bounded by 1/2. Then we can embed this xt into the shift on the Hilbert cube. This is a conjecture for general case. This still remains open. Okay, I stop here. Thank you.